Hi everyone. I've had a request to do an additional video or maybe some additional material on the pumping lemma, and so I wanted to go ahead and make this just so that everybody could have one solid run through on what the pumping lemma really accomplishes, how we apply it, and really the secret sauce that makes it special. So I'll just jump into it. So we are discussing the pumping lemma. Alright, so, and yes, I'm going to try to make it humorous and say that I know in class I always say the pumping llama, but there will be no llamas in this presentation. Okay, so we will not use pumping llama because I don't want anybody to get confused. Okay, let's just go to the next slide. There may be some llamas involved. Alright, so the pumping lemma accomplishes a very important task in this class. We've spent so much time looking at the class of regular languages. It's a set of languages, and to prove membership into that set, we would take a language and go, well, is it regular or not? And in order to prove that it's regular, we would build a DFA, and that would show that it is regular. Alright, that proves it. When we can build a DFA, it proves set membership. However, what the pumping lemma does is it proves that it's not a member of that set. It proves that it is outside of that circle of regular languages in our standard language diagram. So yes, Judgy Llama will judge you if you try to prove that a language is regular without... Oh, I'm sorry. We'll try to judge you if you try to prove that a language is regular with the pumping lemma. This only shows that languages are not regular. So let's look at an example. Alright. So with the pumping lemma, this is what the pumping lemma looks like. The pumping lemma says if L is a regular language, there is a number P, which will never be defined, called the pumping length, such that any string S that is included in L whose length is greater than P can be divided into three parts, X, Y, and Z, such that the length of Y is greater than 0, the length of XY is less than or equal to P, and that X, Y to the I, Z is included in L for all I greater than or equal to 0. Alright, so this Mathanese is ridiculous without an example. So when I said I'm going to show you an example, I'm going to show the pumping lemma through an example. So let's take a simple language. The language that we're looking at is A to the N, B to the N, for all N greater than or equal to 1. So whenever we're trying to solve a whenever we're trying to solve a problem in STEM, we do step 1, understand the problem, step 2, enjoy solving it. So as we try to understand it, we start thinking about the strings that are included. So the strings that are included are, well, you've got AB, that's when N is equal to 1, AABB, that's when N is equal to 2, AAABBB, that's N is equal to 3, AAAA, BBBBB, I'm sorry, AAAA, BBBB, right? 4 A's, 4 B's. You get the idea, so on and so forth. There's some number of A's followed by the same number of B's. So in class, we tried to build a DFA for this. I actually bet you half of a cow that it would not work. And yet we failed to build a DFA. But does that mean that the language is not a regular language? Does it mean it's like us trying to build a DFA? Does it show that it's a not regular language, a non-regular? It doesn't do anything. No, it doesn't show anything. If we want to really determine whether or not it's regular or not, we must apply the pumping lemma. So, step 1, for proving that the language L, where it's A to the N, B to the N, is not regular. Step 1, assume that it's regular. Okay, that's super easy. Let's assume L is regular. Done. Alright. Now the step 2 is to choose a string that we're going to give the name S such that it is included in our language L. In other words, it's part of the language. It needs to be AB or AABB or AAABBB, right? It has to be included in the language, A to the M, B to the N. But it has to have a length greater than P. But how long is P? All right, so this is so important. P will never have a number. It's not 4, it's not 5, it's not 7, it's not 7 million. It is an arbitrarily large number that's never going to be quantified. It will never be anything but P. So when we take a string like, we can try the string S to be A to the 4, B to the 4. Is A to the 4, B to the 4 in the language L? Absolutely, because that's A, B, 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 B. That's in the language L. However, what is the length? The length of that string is 8. 4 A's, 4 B's, 4 plus 4 is 8. And we have this constraint when choosing S. It has to have a length greater than P. Well, is 8 greater than P? I don't know. I have no idea. But probably not, because P was supposed to be arbitrarily long. So how can we choose a better string? The key is to put the string itself in terms of P. So let's choose a string S is equal to A to the P, B to the P. Now in this case, is it in the language L? Absolutely. It's A, B. All right, I can count them off from 1 until P. There's PAs, and 1 to PBs. There's the same number of A's and the same number of B's, because remember, P is a number, right? And that same number of A's and the same number of B's. It is in the language L. However, the bigger thing is, what is the length? Because if we choose an S such that it's in the language L, and it's greater than P, we have a string that we can use in the pumping lemma. Well, what is the length of A to the P, B to the P? Well, there's PAs and PBs. If there were 4 A's and 4 B's, you would have 2 times 4. So if there's PAs and PBs, that means you have 2 times P, which is greater than P. So we have a string S, which is included in the language L, whose length is greater than P. All the mathanese of the pumping lemma that was here, right? There's a pumping length. We have a string S that's included in L with length greater than or equal to P. All right, that's great. All right, we are going far. We're going places. Happy llama is, in fact, very happy. So let's keep using the pumping lemma. So let's remind ourselves, we're trying to prove that language L, which is A to the M, B to the N, is not regular. So step 3, this is where it gets a little funky, okay? But it's our second most important observation. We're going to divide the string into 3 parts, X, Y, and Z. We're going to make little substrings. We're going to divide that string up into 3 parts, X, Y, and Z. Now here's the limitations, and this cannot be more important. It's all the way from up here with the 3. 1, 2, and 3. The 3 parts. One is that the Y has to be greater than 0, and X and Y has to be less than or equal to P. So let's think about this. Y has to have something in it. The length of X and Y, the first 2 parts of the division, have to be less than or equal to P. So let's think about this string. We had the string S is A to the P, B to the P. Let's visualize it as this. S is equal to A's and B's. How many of them? There's PA's in the front, PB's in the back. Now as we divide this string up, they have to be in order. X, then Y, and then Z. Now Y has to have at least one character. X can be empty, it can be however big, but look at that second, what's in blue. It says that the length of X and Y together must be less than or equal to P. So that means it has to be from the first P characters. And since Y has to have something, Y can only contain A's. We're dividing up the string. Y has to have something. X and Y has to be less than that length P, so we can only go into the first half of this string. Y can only have A's. This is so important. That's the thing, is now we're done. The last part of the pumping lemma. All the way back here we had 3 parts. What Y could be, what X, Y can be, and then what's called the pumping lemma, that number 3, right? It says X, Y to the I, Z is also included in L. So let's apply this last part. The last part says X, Y to the I, Z is also included in L for all I greater than or equal to 0. That means we're going to take our little divisions, what we made X into, what we made Y into, and what we made Z into. And Y, we get to change the number of instances of Y. So it'll be X, however many that was, then Y to the I, which would say it's 0, right? And then Z. Well, whenever we take out Y, it changes the string. It makes it to where it removes that string. And it has to be something, right? The length of it had to be greater than 0. So it has at least one thing in it. And that one thing is at least one A. And when it takes away that A, it doesn't take away the B. The other, I think, it can increase the number of instances of Y. So there can be 2 or 3 of the Y's. And when it does so, as we increase I, it increases the number of A's without increasing the number of B's. Every single time that we pump that number I down or we pump the number up, it results in a string that is not included in L. Thus proved. Thus proved. We have applied the pumping lemma, and we have proven that the language L, A to the N, B to the N, is not regular. We did so by following this ultra Mathanese looking thing. If L is a regular language, so we assumed that it was. There's some number P, okay, some arbitrarily large number, such that a string S that is included in L has a length greater than P. I've got that. Yeah. So we made A to the P, B to the P, so the length would be greater than P, and it's included in L. They can be subdivided in 3 parts, X, Y, and Z, such that Y has to have something. X and Y can only be the first half of that string because there's only PAs. So therefore, whenever we increase the number of instances of Y, which it can only include A's, it should have also been included in L. But they weren't, because when we increased or decreased the number of A's, it was not in the language. Thus proved. Okay? This is an application of the pumping lemma. Now, you should be proud of yourself, alright? Pride Llama is proud of you, so you should be proud too, alright? It is a great thing to have this to solve that things are not regular. If you want to know how it works, here's a very short explanation of it. You see, DFA, deterministic finite automaton, means that there's a finite number of states. But these strings, they can be infinitely long, or at least arbitrarily long, if you get my drift. So the reason we can't quantify P is because it's saying, no, there's some number out there, and it can get big enough to do this. What it means is when we subdivide a string S into 3 parts, X, Y, and Z, we're calling the path from an initial state to some, we'll call it a loop state. We'll cover all of the states necessary to get the substring X. And that some path from the loop state all the way to the end will give us the substring Z. But what's crazy is there's at least one loop in there. And that loop has to be finite, P, right? It has to be finite. It can be large, but it has to be finite. And it has to loop back to itself in order for all of this stuff to work. If we prove that no such loop exists, then we prove that the language is not regular. And that's what that third condition did, is it showed that, okay, if you have a valid loop, then it must be valid. It must be able to be produced. And this is why the pumping lemma works. So, a couple of tips and tricks. It's all about picking S. You will find that applying the pumping lemma is very repetitive. You just need to pick an S that's inside of the language, and you need to do it in a way that Y can only have one character most of the time, okay? You might need some, as you get more advanced with pumping lemma, it might be there. But think about palindrome, right? The palindrome was taco cat, the same forwards as it is backwards. Is this a regular language? Can we build a DFA to accept? Look at the string. A to the P, B to the P, B to the P, A to the P. It's in terms of P, it's longer than P, and it's in the language. Right? It's forwards, backwards, it's the same. Backwards, forwards, it's the same. Oh, taco cat. Right? It's in the language. It's in terms of P. And here's what's crazy. Since the length of X and Y has to be less than or P, and Y cannot be blank, Y contains only A's. When we pump up, there's going to be A's on the front and not A's on the back. It won't be in palindrome. Thus proved. Done! We just proved palindrome, even though it was exactly the same. That's your big tip, that all of them are exactly the same. It's just repetitive use of the same proof. And with that, we're done. That's all there is to the pumping lemma. In order to prove something's non-regular, we apply the pumping lemma, and that's it. And I promise, no more lemmas, no more llamas. Alright, okay, some more cute llamas. And also, we're going to have some more lemmas too. As is always the class, we're getting larger and larger. This class goes from the regular languages to the context-free to the Turing languages. So you better believe that there's something very similar to the pumping lemma for context-free languages. But here's what's crazy. After the context-free languages, it's going to be the Turing languages, and then we're going to talk about computability. Fundamental things for our field. So that's it. That's the pumping lemma. I hope this helps everybody that needed just one more look at how the pumping lemma works.